Hello, everybody. In this video, I will go over those problems on practice test number 3, which is on chapter 4, applications of the derivative. So this test is going to have many application and theoretical topics. And so it will be challenging, and that's why I am creating this video. I hope you will benefit from this. I hope you will go over each problem carefully to make sure you understand the concepts introduced in chapter 4. All right, so before we begin, let's just make sure we understand we are talking about the same problems, okay? So I will be going over these exercises in Math 211, Calculus 1, practice test number 3, which you will see right here. This is under the chapter 4 module, of course. And this is based on chapter 4 of the OpenStax Calculus Volume 1 for Calculus 1. And so I will start by, and by the way, I just wanted to tell you, chapter 3 was all about how to differentiate functions. Chapter 4 has important concepts. Some of them are pretty deep, as well as the two famous types of word problems. One has to do with related rates. The other has to do with maximum and minimum or optimization problems. So as it says here, the test will be difficult, okay? And so please expect a challenging exam. But by preparing and just going over these problems, I hope you will be able to do fine. All right, so let's start with chapter 1. And of course, I did not mean chapter 1, I mean problem number 1. All right, so problem 1 is true-false questions. We have 10 questions or 10 sentences there, and you are to put true or false for each one. And let me just say, the true-false questions are one of the best ways to really understand or to figure out if you're understanding these concepts. All right, so listen very carefully to the explanations. All right, so question number 1, part 1 says, any critical point of a function, at any critical point of the function, the derivative must be 0. So it says any critical point. Okay, so it says if x is a, let's say if x is a critical point, it says the derivative at x must be equal to 0. All right, is that true? The answer, it's false, okay? No. And why is that? By definition, a critical point has to be either where a point where the derivative is 0, or it could be undefined, right? All right, so that's why this is false. Remember, the problem nowhere says that the function has to be differentiable. If the problem said the function f is differentiable, then every critical point has this property that f prime is equal to 0. Because remember, the definition of a critical point is where the derivative is equal to 0 or undefined. Number 2, every critical point represents a local maximum or a local minimum. So does the critical point imply that it has to be a local extremum? And the answer is false. All right. Can you think of a critical point that is not a local extrema, or local maximum or minimum? Neither maximum nor minimum. And the answer, yeah, you can probably think of something like that, right? An easy, probably the most important example would be x cubed. F prime is x cubed. The derivative is 3x squared, which is 0 at x is equal to 0. But of course, so in other words, this point, when x is equal to 0, this point 0, 0 is a critical point, but not local maximum or minimum. And you can easily see that is true from the graph. Number 3 of problem 1, every local maximum or local minimum occurs at a critical point. So it's the opposite of number 2, or the converse of number 2. When you have a local extremum, does it mean that it has to be a critical point? And the answer in this case is yes. There is a theorem that says if you have a local extremum, which has to be in a internal point of an open interval, the definition of a local maximum or minimum for our purposes in this class requires that the point be an internal point of an open interval, because the word local has to do with a point in an open interval, right? It's a lowest point or the highest point on an open interval. So if you do have that, if you have a local maximum or minimum, it has to happen at a critical point, whether the derivative is 0 or undefined. So the answer in this case is yes, by a theorem about local maximum and minimums. Number 4, every absolute maximum and minimum occurs at a critical point. So this is absolute extremum. Does it have to happen at a critical point? And the answer is no. Think of a function like this. Now, this is a very simple function. Fx is equal to x on an interval from -1 to +1. All right. And so clearly, this is the maximum point, and this is the minimum point. But remember, there is no critical point for this function because the derivative is always defined and is equal to 1. So the point about an absolute maximum or an absolute minimum is that it could happen at a critical point if it happens to be inside of an open interval, but these things could also happen at the endpoints, right? Which is why, in order to find absolute extrema, you had to check the values at the endpoints. That's a very important concept you learned in chapter 3 or chapter 4. Okay, number 5, every differentiable function has an absolute maximum and an absolute minimum. So if f is differentiable, does it mean f has absolute max and minimum? And the answer is no. Again, this is a great example, okay? You have the straight line, and if you don't define a specific interval, this is defined for all x, the entire real number system, and clearly there is no maximum or minimum. Infinity, by the way, is not a number, and negative infinity is not a number, and so they do not qualify as a maximum or minimum value. Okay, the point about this is, with an additional information, with an additional requirement, okay, this could be true, and that is if f is differentiable, and if f is continuous, it doesn't even have to be differentiable. If a function is continuous on a closed and bounded interval, such as this one here, this is a closed and bounded interval, then the function will have an absolute maximum and an absolute minimum. It's called the extreme value theorem. Okay, but as it stands, if you do not have that closed and bounded interval, you may or may not have a maximum or absolute maximum or absolute minimum. Actually, even this one here, if you think of this on an open interval, -1 to +1, if the interval is open, you notice here it's this graph with an open circle on both ends. You notice that this doesn't have a maximum or minimum. Well, you say, well, yeah, the maximum value is 1 here. Well, no, it doesn't quite get to 1, right? Because it's an open interval. X is equal to 1 is not included in this interval. So there's actually no maximum or minimum. So an open and bounded interval does not do. The function has to be defined on a closed and bounded interval in order to have a guaranteed maximum and minimum. Absolute maximum and minimum. Okay, number 6, at every inflection point, the second derivative must be equal to 0. So you have an inflection point. Does it mean that the second derivative has to be equal to 0? Now, this is a little tricky. And let me just explain why this is a little tricky, because it sort of depends on who you listen to or what book you read. For our purposes, if you read our definition of an inflection point in our book, the answer is no, because the second derivative does not even have to be defined. So what is an inflection point? If you look in the book, and if you look at my lecture notes, you'll see that an inflection point is a point on a continuous function, and the function has to be continuous at that point. And it doesn't have to be differentiable, by the way, surprisingly. It's a point on the continuous function where the concavity changes. So the concavity changes means the concavity has to go from up to down or down to up, like, like right here, right? And so how could this be possible if the second derivative is not equal to 0? So an example, this is a sort of a tricky example, is x to the 1/3 power. The graph is, of course, this is the inverse function of the x cubed power. The graph goes like this. Okay. Now, what's going on here? This is definitely an inflection point because the graph goes from concave up to concave down. All right. But what happens is the derivative, the derivative is 1/3 x to the negative 2/3, which is 1/3 to the x to the 2/3. This is undefined, so this one does not exist. F prime of 0 does not exist at x is equal to 0. All right, so the derivative is not defined, and therefore the second derivative is clearly not defined, but it is an inflection point. Okay, so in many, in fact, most inflection points, you could say that the second derivative is 0, and if it exists, it will be 0, but there is no guarantee that the second derivative exists, not even the first derivative. Do we know that exists? Okay, so that's tricky. Number 7, at every inflection point, the first derivative cannot be 0. Is that true? So if you have an inflection point, does the derivative have to be non-zero? And the answer is no. So what's a good way to think about this? Well, there is one way. I mean, we already give an example where you have this function where the derivative, well, I guess in this case, the derivative is undefined, so it is non-zero. So maybe that doesn't work. But how about this function here? That's why f of x is x cubed. Okay, again, this is an inflection point. The second derivative is 0, but the first derivative is also 0 at the inflection point 0, 0. Okay, so an inflection point could be a critical point as well. Okay, number 8. Right? If the derivative is positive for every real number, the function is increasing everywhere. Okay, so if the derivative is positive everywhere, at every single real number, the function is increasing everywhere. And the answer is yes. And this is a result of the mean value theorem, that if it's not increasing everywhere, then there would have to be a point where the derivative is 0 or less than 0. All right, number 9. If the second derivative is positive for every real number, the function cannot have an inflection point. Okay. If the second derivative is positive everywhere, what does it mean? Well, that means that it's concave up. Okay, and it's always concave up, right? Number 9 says if the second derivative is positive everywhere, the function cannot have an inflection point. What happens at an inflection point? Well, if at the inflection point, if the second derivative does exist, it has to go from positive to negative or from negative to positive. If the second derivative is always positive, then it cannot be 0. And so it will always be concave up and there is no inflection point. So the answer is, it is true. Yes, the function cannot have an inflection point. Okay, so number 9 is true. And finally, for this problem number 1, the last one is number 10. A constant function has no local or absolute extrema. So if f of x is constant, right? So you have a constant function like this. Does it have any local or absolute maxima or minima? It's really tricky. Okay, but if you think about this, okay, look at the definition of a local maximum. Local maximum, so a local maximum is a point where, let's say, local maximum occurs at x is equal to a if f of a is greater than or equal to f of x for all x. in an open interval containing A. So if you can find any open interval of A, open interval containing A, where f of A is bigger than or equal to any fx for all x in this interval, then we call this a local maximum. So this point, okay, listen carefully. By definition, this, because it is equal to f of x for all x in the interval, it happens to be a local maximum. Did you get that? Every point on this graph is actually a local maximum by definition. Well, then is that always going to be a local minimum also? Yes, because of the definition. A local minimum is, of course, this, this becomes the other way, right? But it still has the equal sign. So by definition, every point is a local maximum as well as a local minimum. And is that the highest point on the graph? Yeah, there is no point that's higher than this, right? So it is also an absolute maximum and absolute minimum. So here, strangely enough, every point is a local max and local min, and represents an absolute maximum and the absolute minimum. What is the absolute maximum of this function? It's C. What's the absolute minimum of the function? It's also C. What's a local maximum? It happens everywhere, and the local maximum is C and local minimum is C. It's a trivial case, but that's what we would have to say by definition. Okay, so we will go to the second part of this video before we go on to number 2. I hope this has been sort of eye-opening to you. Oh, before I finish this part, I should say number 10, the answer is no. It is false because the number 10, the sentence says a constant function has no local maximum or absolute maximum. Or actually, it says a constant function has no local or absolute extrema. And the answer is it has everything. A constant function has a local maximum, local minimum, an absolute maximum, and an absolute minimum. And they all happen at every single point. Okay, now let's go to the second problem.